All right, so we saw kind of the basics of these hydrohalogenation reactions, um, but now we're going to delve a little bit more into the stereochemistry of this reaction and also look at the energetics. We're going to do the same hydrohalogenation, but remember, what is a deuterium? A deuterium is just an isotope of a hydrogen. That means that it reacts the exact same. So just like last time, we have our partial minus on our bromine, our partial positive on our deuterium. So the mechanism is going to work the exact same. At this point, we'll draw that mechanism, but we're going to think more about the stereochemistry this time because we're going to have stereocenters that are created. So that pi bond is going to be attracted to that deuterium. It's going to add there, and that deuterium-bromine bond will then break. So that's going to create a carbocation on the side that the deuterium was not added to. And then is the deuterium going to be drawn as a wedge or a dash, or will it be either option here? Yeah, so essentially if we look at our starting material, the deuterium can add to this face or this face. So it could be a wedge here or a dash here, and it's just based on whichever side it bumped into. So it's going to make a mixture of both the deuterium here and the deuterium going onto the back face. So both the wedge and the dash. So at this point, we have our carbocation, and we have Br minus around. So the Br minus is again going to be attracted to that positive charge. And I'll just show it with this one because it's the closer one. And which face is that Br minus adding to? Well, it would be adding to the top face if it ran into that face, or the bottom face if it ran into that face, right? Because what's the hybridization of this carbon? What's the hybridization here? All right, you've thought about it, you've made your selection. This is sp2 hybridized. So this would be a trigonal planar carbocation, and that means that it's essentially a situation where there's just an empty p orbital on either side, and that bromine, it's just floating around in solution, right? And if it runs into this face, it's going to be on this side. If it runs into this face, it's going to be on that side. So that's all that is going to determine whether it's on the top or the bottom face. So if the bromine adds to the top, it's going to make this here. And if it adds to the bottom, it's going to make this here, right? So it's going to make a mixture of these two molecules. What's the relationship between these two molecules? Yeah, they're diastereomers. So we'll just label this A, this B, and A and B are diastereomers. Are we done? Is that all of the products that are possible? No, we also have to take care of this molecule over here, right? The bromine, the Br minus of the bromide ion, is also going to add here, and it can do the same thing. It can add to the top or the bottom. So I'll draw the top here. So again, the wedge. If it added to the bottom, it would be the deuterium was on the wedge side, and the bromine is down there. It would look like that. So we have A, B, C, and D potential products. Are any of these identical to one another? Well, we already said A and B are diastereomers. What is the relationship between C and B? Yep, C and B are enantiomers. And what's the relationship between C and A then? Diastereomers. What's the relationship between A and D? Yep, those are enantiomers. So again, make sure you're writing these things out. You should be able to tell me the relationship between all of those different molecules. And then what kind of product mixtures do we have here? As far as the terminology of these addition reactions, we saw that we can call things syn, we can call them anti. So which of these are the syn products and which of these are the anti products? All right, you've already drawn which ones are syn, which ones are anti. Remember, syn means that things are added to the same face. So this would be syn addition, this would be syn addition, this is anti addition, and this is anti addition. Anti, again, just means that they're on opposite faces. So hydrohalogenation makes both syn and anti products, anti-addition products. So that's kind of the situation with the stereochemistry. We can make all the different possibilities when stereochemistry is important. With the first example that we talked about previously, we didn't talk about stereochemistry here because there actually isn't there's no stereocenter created in that molecule, so there's no need to talk about stereochemistry. In our two rules of organic chemistry, negatives flow to positives and the ball always rolls downhill, we said, how do we know that the ball is rolling downhill? Well, we're getting rid of a weak pi bond and making strong sigma bonds. And we can also quantify that by looking at bond association energies. So that's what I've done here, is put into the course note packet. We broke a pi bond and a sigma bond, and we made two different sigma bonds. And when we look at the difference of the energy of the bonds that were broken versus the bonds that were formed, our delta H value is negative 60 kilojoules per mole. So again, the ball is rolling downhill in this reaction. This is an exothermic reaction, which means it's favorable.